All right, today we're going to take a look at 5.7, and we are going to be working inside of the trig universe, right? So one of the things that I imagine you do remember from trig, but you haven't thought about in a while, is something called SOHCAHTOA. You know what I'm talking about? Okay. We're going to make use of it today, so let me mention it right now in case it's something that you haven't thought about in a while, or maybe your trig or pre-calc teacher or whatever didn't teach it this way, and that's okay too. So this S right here is for sine. The C is for cosine. And the T is for tangent. Okay, so that's what the beginning letters of each of these stand for. And all of this talks about the relationship of sides in a triangle, which we will be looking at today. So let me draw a triangle. And we're talking about right triangles specifically. Pretend that's a right triangle. It's kind of not really looking like it, but pretend. Okay, there's a right triangle. And we need a reference angle. I'll call this my reference angle theta. Okay, so if this is angle theta, this is the side that's opposite it. This is the side that's adjacent to it. And then the third side is the hypotenuse. Okay, everybody good with that so far? So each one of these SOHCAHTOA, these three pieces, stands for one of the trig functions and its relationship within the triangle. So the first one is that the sine of theta is the opposite over the hypotenuse. There we go. And then the next one is that the cosine of theta is the adjacent over the hypotenuse. And then the last one is that the tangent of theta is the opposite over the adjacent. And while they're not written in here, because this usually shows up in a geometry class, that's where you usually see this for the first time. Maybe you didn't, but that's where I saw it for the first time, was a geometry class. And we talked about these triangles and this relationship. But in geometry, we don't usually go any further than these three trig functions, but there are three others. They're the reciprocals of each of these. For example, we have cosecant of theta, and oops, I forgot the C, cosecant of theta. And it's the reciprocal of sine, which means we take the opposite of the hypotenuse and we would flip it upside down. So you can think about this as 1 over sine of theta, or you can think about this as then being the hypotenuse over the opposite. We have secant of theta, so secant theta goes along with cosine, so the co and the c, the c's and the s's kind of are opposites, right? So sine and cosecant, it's a sine and a co-function. And then over here we have a cosine and a secant function. The c's and x's go together. And this one is 1 over the cosine of theta. So we could also understand or remember that this is, instead of adjacent over hypotenuse, it would be hypotenuse over adjacent. And then the third one is cotangent. So the cotangent of theta would be 1 over tangent of theta. There's also other relationships between between cotangent and tangent, and then the sine and the cosine. That's not what I'm showing on here. We're just looking at the triangle parts. And this could be done, instead of being opposite over adjacent, it would be adjacent over opposite. Okay, is all that good? Okay, so that's one remembrance that I want you to have. The second one that's most closely related to where we're going to begin is what I'm going to show you next. And this one is graphs. So let me get a graph paper up. There's the graph. All right. That's smaller than I wish. That's really bigger than I wish. There's a medium one, but I'm not seeing it in here. What about that one? No, I don't like that one. Let's go back to, oh dear. All right, we'll go with that. I think that'll work. All right, the four, well, there's 6 graphs. The 3 that I really want to draw primarily, but I'll draw all 6 of them, are the graphs of sine, cosine, tangent, and then secant, cosecant, and cotangent. Okay, so let's do sine first. If I'm going to do the graph of sine of x, or sine of, yeah, we'll do sine of x, we'll write it that way. And these grid marks are going to be, this feels like too small. we're going to go with it because I want to put more of them on one page than I can fit on the other one. So we're going to let this be the value 1 right here, and this one's going to be -1. And each of these grid marks on the x-axis are going to represent our pi over 2 values. I think that's what I want. Yep, it is. And so this one would then be pi, and then I have 3 pi over 2, and I have 2 pi. So if I'm dealing with sine, the sine graph looks something like this. Hang on. Seriously. Move that up. Okay, the sine graph looks something like this, and I'll do it in red. It goes through the origin, and then it goes up to 1 at pi over 2, down to pi, and then down to 3 pi over 2, and back up to 2 pi. And it repeats this oscillating fashion on either side of the axis at these same intervals. So my graph looks something like this. Okay, everybody remember that one? All right, the cosine graph is really just a shift of this graph. You don't always think about it that way, but it is. Okay, we'll do it over here. Same grid marks that we had before. I won't be able to go quite as far over there if I do that way, but that's all right. So this one, almost, is still pi over 2, pi, 3 pi over 2, and over here is 2 pi. And the same thing on the left-hand side. We'll go up to 1 and down to -1. But with cosine, we don't start at the origin. We actually start at a peak on the y-axis, like this. And it goes down, down, up, up. And we get a graph that looks on the same side. We'll do it over here, down, down, up, up. And so our graph looks something like this. Okay? And again, one way you can interpret this or think about this is if you took the sine graph and you simply shifted it pi over 2 to the left, you'd actually end up with the same graph as the cosine graph. We call these graphs also sinusoidal. That's another phrase that we see. I'm going to draw, let's use the next grid. Let's do tangent next. So the tangent graph has a lot of repeating asymptotes. That's something that's different about this graph. There's asymptotes. And the asymptotes occur at every pi units, but they start at pi over 2. So again, can I stop marking my axis and we're okay with the fact that all of my x-axes are always at pi over 2? You guys good with that? Okay, so if I do that, then the first asymptote's going to be here. Hang on, let me move it because I got it shifted a little too far to the right. There. The next one would actually be on the other side, would be over here at -pi over 2. And then they're at every pi after that. So I'll draw a couple more of them in here. I think that's okay. And they're going to keep repeating. And the tangent graph goes through the origin, just like the sine graph did. And it kind of looks like an x cubed graph, except for the asymptotes. And it has this repeating feature like this. Is that all right? And then my tangent, or my cotangent graph, also has those same asymptotes going on, or that is, it has asymptotes going on. And they're still occurring at every pi units, but they don't start at pi over 2. They actually start at the origin and at the whole pi values. So you get them occurring like this. That's okay. And it won't be easy to see it, but I'm going to draw it. I'm trying to draw it to the left of this a little bit. Oops. There's one right on the y-axis. I'm trying to draw it a little bit to the right so you can see it. But the graph, instead of increasing from left to right like the tangent graph does, it has x-intercepts halfway in between each of the asymptotes. That happens. But instead of increasing from left to right, it actually decreases. So it goes like this. Okay, all good so far? Okay. Your calculator can remind you of these graphs. There's nothing about them that your calculator can't handle. If you are graphing trig inside your calculator, zoom trig is going to give you those nice pi over 2 intervals along your x-axis instead of it doing it 1, 2, 3, 4, and so forth. All right, our last two are cosecant and secant. Okay, so these actually will have asymptotes as well. And they're going to occur, that is the asymptotes, at every location that the corresponding sine or cosine graph had an x-intercept. So over here, sine of x has an x-intercept at the origin. So its reciprocal, which is cosecant, is going to have a vertical asymptote at the origin. So we're going to have, again, this is going to be one that I can't draw very well, so I'll draw it to the side and I'll kind of shift it over there. It's going to be right here. Hang on, I grabbed too much. It's going to be right here to the side of the y-axis, okay? But it's really on the y-axis. I just can't draw it that way. And then it's going to occur at the next value. So the next x-intercept is at pi, right? And the next one is at 2 pi. So just like with cotangent, actually, it's occurring at every pi, whole pi value. So we have one here, we have one here, and it goes over here and over here, like so. All right. Now, the other points of interest from the sine graph are the maximums and the minimums. So if I take the reciprocal of the number 1, it's still 1, and the reciprocal of the number -1 is still -1. So all of these peaks and valleys are still going to occur as values of 1 on my cosecant graph. So again, I'll mark this one right here as 1, and this one is -1. And we have points, let's see, it was here, and then we have one here, here, and here. But reciprocals means that everything that was a fractional value, right, something small between 0 and 1 is going to become large. So these end up looking sort of like trapped parabolas. And it has this repeating pattern, just like the sine and the cosine graphs and tangent and cotangent do, right? It's just cyclic. It keeps repeating the same pattern over and over again. And the last one is secant. So we still have to draw much the same as we've already drawn on the other 5. Going to have asymptotes like on the 3 other previous to this one. The asymptotes, this goes back to cosine, are going to occur at every value that cosine is equal to 0 or on the x-axis. So it's going to occur at the pi halves values, right? So at pi over 2, at 3 pi over 2, and correspondingly on the left-hand side. So we're going to have asymptotes at every pi halves values. Well, at the pi half values, pi apart. So this one's at pi over 2, and the next one, it's not drawn well. It's better. The next one's going to be drawn at 3 pi over 2. We're going to have one at negative pi over 2 and at negative 3 pi over 2. And I want one more in here, and since my picture has more space on the left, I'll put it on the left. But it keeps going on. And again, at every values of 1 and -1, I'm still going to get the same numbers, right? Because the reciprocal of 1 and -1 is the same. So at x equals 1, which is on the y-axis, I didn't say that right. At y equals 1 on the y-axis, I'm going to have another y equal 1 value here. And then based on that, I can fill in the rest of them because the pattern remains the same as it was before. And I have, again, what sort of looks like trapped parabolas. These are not drawn lovely, but for what I need them for in a moment, I think they're okay. Okay, everybody good so far? That's our brief pack backwards into trig. It's not super brief. It was 15 minutes, okay? But I think you're going to need it for what we're going to do next. So back in section 5.3, we talked about something called inverse functions. Shake your head if you know what I'm talking about. That entire section was algebra, right? We switched x's and y's, and we solved for the new y. We verified them by doing composite functions. Everybody remember that? Okay, so back in that section, what was the condition from an algebraic standpoint for something to have an inverse?
It's 1-to-1.
Had to be 1-to-1. And if you look at the 6 graphs that you just drew, none of them are 1-to-1, correct? 1-to-1, one way of thinking about it is none of them are going to pass the horizontal line test. Every single one of these, if you draw a horizontal line through them, are going to fail the horizontal line test. However, we are doing inverse trig functions. That's the title of this section. So what gives? Well, what gives is that we're going to restrict the domain. So I'd like for you to start with the sine graph and think about, if I cut the sine graph into a smaller portion, and I only looked at a portion of it, I would have a one-to-one graph. The portion that we're going to cut it at is going to be from here to here. And if I look only between the blue lines, it is one-to-one, correct? So in particular, this went from negative pi over 2 to pi over 2. So when I'm talking about inverse trig, specifically inverse sine functions, my domain will only be from negative pi halves to pi halves. In terms of the unit circle, what we'll be talking about is which quadrant we're in. So if I am from negative pi halves to pi halves, and I'll remind you, this is quadrants 1, 2, 3, and 4. Do you guys know why it's actually labeled in that direction? This is a fun fact for your day. It's a freebie. The first person who started this sort of construct that we continue to use was left-handed, and they went around in the other direction. So Levi, this one's for you. That's right. I at least know Levi's left-handed because we've talked about it. Okay. So on my sine graph, I'm going to be inside of quadrants 1 and 4 because pi over 2 is the top of my unit circle and negative pi over 2 is the bottom. So for sine, I'm going to be in quadrants 1 and 4. Okay, cosine. Where does it seem like it would be nice to restrict our domain to being on this one? What looks like it would make sense? 0 to pi, and you're exactly right, that's what we do. We're going to do 0 to pi, like this, which means cosine values are going to be in which quadrants? 1 and 2. So 0 is at the x-axis on the right-hand side. Pi would be at the x-axis on the left-hand side from a unit circle perspective. So when I'm looking at arc trig functions or inverse trig functions, I'm going to be in quadrants 1 and 2 for cosine. Okay, where am I going to restrict them on these? Let's do tangent. Where am I going to draw those blue lines?
Negative pi half, pi half.
Yeah, negative pi halves and pi halves. It's going to be exactly like, that's not drawn well, but it's going to be exactly like what I did for sine, which means I'm going to be back in, and I didn't list these on there before, but I will here now. So here I'm going to be in quadrants 1 and 4. Here I was in quadrants 1 and 4. And over here I'm in quadrants 1 and 2. Right? What about cotangent? Where are my restrictions going to be? 0 to pi, right? So cotangent and cosine are matching up. Tangent and sine are matching up. So this is 1 and 2. Quadrants 1 and 2. I don't get to just mark it at the asymptotes for secant and cosecant, though, do I? I've got these trapped parabola-shaped things, and if I do from one asymptote to the next asymptote, I definitely don't have a one-to-one function, right? So the breaking apart is not going to be pretty. We're going to break apart not on asymptotes here. So we're actually going to break this apart. Let me make sure I get it right. We're doing cosecant. On this one, it's going to be, whoa, I meant to do a line tool. At negative pi over 4, come on, to pi over 4. If I look between the blue lines, aside from the fact that it's awkward feeling, is it 1 to 1? It is. So this is quadrants 1 and 4. So cosecant goes along with its reciprocal sign, okay? And then over here for secant, I do the same sort of thing. I'm going to mark it at pi, 0 and pi. So I'm going to be in quadrants 1 and 2. Okay. All good so far? Now we're ready to start the notes proper. Let's go back to page 1. Today we're looking at inverse trig functions. They're also called arc trig functions. We are going to use arc trig functions for this course. I might slip up and say them the other way around. Please forgive me if I do. The reason is because when we write inverse trig, we use a -1 sort of in an exponent location. And because we use exponents for so many other things, it can get kind of muddy. The waters get a little bit muddy by doing that. So we're going to use arc to do so instead. So we have 6 arc trig functions: arc sine, arc cosine, arc tangent, and then arc cotangent, arc secant, and arc cosecant. Adrian.
The range and the domain look switched there.
So these are the range and the domain of the arc functions instead of the functions we just drew. So you're exactly right. The domain and the range are switched from the values that we just looked at. So everything that we looked at in terms of what the x values and y values are gets switched, because that's what inverse trig functions do. They switch inputs and outputs. So previously, when I was looking at sine, the range was -1 to 1. Now for arc sine, that's the domain. Previously for sine, the domain was -π/2 to π/2. Now that's my range. Everything's switched. That's why I wanted to show you all of that, is because I wanted you to see where it's coming from. We're not making anything up. We're just switching x's and y's. So we have arc sine, arc cosine, and arc tangent here. And notice I've put the quadrants in over here just like we did on the graphs, right? Which quadrants are we in for these? Okay, I have the next 3 on the next slide. Is everybody done with this slide? Not quite. Okay. Good. Good, Connor? Okay. So here's our other 3. So I have tangent, secant, and cosecant. Do recognize my notes actually here have the secant and the cosecant in the opposite order of what I just drew my graphs a minute ago. And don't get confused about that. Just pay attention to what the actual names are instead of the numbering of them, if you will. And again, everything switches. The quadrants are exactly what we said that they should be in order to make this work. So much like every section we've done, maybe not every, but just about every section we've done here in Chapter 5, we're first looking at the algebra, in this case the trig component of what we've done in the past. And maybe you have and maybe you haven't done it, but that's the idea, is that it's a pre-knowledge kind of thing to calculus. And then we're going to look at the calculus component, which from the title, if you look at the very top of your page, said that we were going to look at differentiation. So derivatives in this section. The lesson on Tuesday will be integrals, okay, antiderivatives. Okay, am I good to switch slides? Yeah? Okay. Now, the first couple that we have, the first couple of examples, actually lend themselves very nicely to the unit circle. If you remember the unit circle, that's great. If you don't like the unit circle, once we get to the third one, we're not going to be able to use it anyway. And I'm going to show you another option with triangles. Okay? So these two first examples, while they can be done with the unit circle, could also be done with triangles. But I want to wait till I get to the third example where I have to use them to show you what that looks like. So from a unit circle perspective, what this is saying is that I'm going to change this in terms of the language on the previous slides. I want to find the sine value, the angle that is, where the sine value is equal to 1/2. But I have to be, remember, in quadrants 1 and 4. Right? That's where I have to be. I'm not going to get multiple answers like you did if you did this in trig. In trig, you would have gotten something like, it's this angle plus pi, and 2 pi, and 3 pi, and 4 pi, because it cycles, right? We won't have that here. We will have just one answer. So we want to think about from a unit circle perspective on these because we can. And I want to be in the correct quadrants. I want to be in quadrant 1 or 4. So is sine positive, because this says sine is 1/2, in quadrant 1 or in quadrant 4? It's in quadrant 1. Real quick reminder, if you don't remember how this works, or a mnemonic to help you remember, ASTC, like this, going around backwards, it's a smart trig class. A smart trig class. You with me? A smart trig class. Yes? What that's telling you is where they're positive. All of the trig functions are positive in quadrant 1. Sine is positive in quadrant 2. Tangent's positive in quadrant 3. And then cosine is positive in quadrant 4. Okay? If that's helpful. If it's not helpful, just ignore it. It's fine. All right, so we are supposed to be in quadrant 1 on this because that's where sine is positive. So sine is going to be equal to 1/2 at one of our two values, either this one or this one on the unit circle. Okay? There's 3 values on the unit circle that show up. These are not drawing my lines very well. Right? It's at pi over 6, pi over 4, and pi over 3. Those are the 3 values. So we have here, here, and here. And from a unit circle perspective, the sine values, when we do an xy ordered pair, sine is y. Cosine is x. Okay? This is a lot of trig. Real quick, like crash course reminder. Which y value is going to be 1/2? Is it going to be this one down here? Or is it going to be this one up here?
The one in the middle?
It's not the one in the middle. The one in the middle are going to be square root 2 over 2 and square root 2 over 2.
That's right.
So those two match. The ones that I've marked have a 1/2 in them. One of them has a 1/2 in the x location, and the other one has a 1/2 in the y location. We're looking for the one that has 1/2 in the y location.
First one.
It's the first one. So this one is 1/2 in the y location. The other one is square root 3 over 2, which is bigger than 1/2, which makes it higher up, so it's in this location. And if you don't remember your unit circle, just go print one off the internet. You'll be able to find one really easy and remind yourself where these angle measures are marked. It will be helpful. Okay, so it is at this one right here. What angle measure am I at when I'm in that first location?
30 degrees?
30 degrees, and in radians that would be pi over 6. So the answer to the question here is pi over 6. The question is asking what angle measure produces the sine value that's 1/2. That's the same question, sort of flipped around. We're going to do one more with the unit circle. Square root 2. So when we see things like square root 2, square root 3s, and 1/2s, like we've seen on these first couple, we've got a couple of those things, unit circle can be used, typically. So this is telling us now I want my secant value, right? This is equal to some angle. My secant value needs to be equal to negative square root 2. Now, I don't know about you, but I don't think in terms of secant very well. Sine, cosine, tangent for me are a lot easier to work in than secant and cosecant and cotangent. So I'd really like to change this to be an expression for cosine because it's the reciprocal function for secant. So if I do the reciprocal on the left by changing secant to cosine, I need to do the reciprocal on the right and flip the fraction upside down. So this is still negative 1 over square root 2. And another way we would see that written, rationalizing that denominator, would be negative square root 2 over 2. Okay? Undo that. So, where do I have, let's see, this is cosine now. Where do I have a cosine value that's negative? Quadrant 2. So remember, cosine, I'm stuck with quadrants 1 and quadrant 2. It's 2 over, or it's negative over here in quadrant 2. And we mentioned before, it's these exactly in half quadrants, right? It's this right here, not quadrant, but location in the quadrant, half and half. So what angle measure am I at all the way, that was supposed to be a different button, all the way over here? What angle measure is that? It is 3 pi over 4. Okay, this is 3 pi over 4. So I have 3 pi over 4 as the answer to this question. Now, how could you check to make sure you're right? This is so easy because your calculator will do it, right? You could take 3 pi over 4 and you could type in cosine, as long as you're in radians, cosine 3 pi over 4, and you hit enter, and it's going to give you the decimal approximation that should be negative square root 2 over 2. Right? It doesn't help you to find this 3 pi over 4. It really doesn't, because you're working with things that are irrational. But it will confirm it for you very nicely. Okay, so if there are unit circle values, you can totally use the unit circle, and that's great. But once we get to problem C, we do not have a unit circle value because 3 over 4, not 3 pi over 4, or something like 3 over 4 is not anywhere on my unit circle. Agreed? So here's what we do. And you could have done this for the last two as well if you didn't like the unit circle approach. We're going to draw a triangle. And we're going to mark an angle in our triangle as our reference angle. This is how I typically draw my triangles. I'm drawing it like, well, actually, I should probably make mention of this. Let me pause just a second. This is drawn correctly, but let me preface this just a little bit. Inside of the Cartesian coordinate system, this one is says sine of arctangent. We're looking at just the arctangent part first, by the way. Ignore the sign on the outside for the moment. Arctangent. Okay, where is tangent positive? Which quadrant? Okay, quadrant 1 and 3. And if I'm working with arc-trig functions, I am stuck in quadrants, that was not a 4, in quadrants 1 and 4, right? So am I going to be in quadrant 1 or quadrant 4? Quadrant 1. That's the reason I drew the triangle the way I did, like this, because I'm in quadrant 1. If I'd had a negative 3 over 4, I would have drawn it upside down, and it would have looked like this, and I would be in quadrant 4. Are you with me? If I were dealing with something with cosine, I'd be over here, and I'd be in quadrant 2 if it were negative. Okay, so you need to know which quadrant you're drawing it in for this to work very well. The gridding, right, the scale, it doesn't matter at all. This is an angle theta. I need a reference angle. The reference angle is always the one that's here in the middle, right, attaching towards the origin. And I want to think just right now about the arc tangent of 3 over 4, which is this theta. And I want to change it into the tangent form. So this is the tangent of theta is 3 over 4. Here's where SOHCAHTOA comes in. TOA, tangent, is opposite over adjacent. This says the tangent of theta is the opposite, 3. So here's my 3. Over the adjacent, 4. And here's my 4. How could I find the third side? Pythagorean theorem. This one's actually a Pythagorean triple that you might remember.
Wouldn't tangent be 4 over 3? Because it's the opposite.
Okay, say that again.
Wouldn't tangent of, or, never mind, it's not switching. I'm tripping.
It's okay. If we had cotangent, we would flip it. Is that what you're thinking about? Yeah. If we had cotangent, we would put the 3 and the 4 in the different locations. But this one I think is set up right. Okay, so we would use the Pythagorean theorem in general. This one's a really nice example of the Pythagorean theorem. We call it a Pythagorean triple. And it's a triangle you might remember. It's a 3, 4, 5 triangle. And if you don't remember it, you just use the Pythagorean theorem to find the value, and we'll do another one of those in a little bit. But the 3, 4, 5 looks like this, okay? We're not going to find the angle theta. We don't care what the angle theta is, actually, okay? What we really want is now that we've drawn this triangle, we want the sine of the angle theta in this triangle. What is sine? Opposite over hypotenuse. The opposite is 3, and the hypotenuse is 5. 3 over 5 is my answer. I never found theta, correct? Why did this happen? Well, it happened because I took a trig function of an arctrig function. It's like doing inverses of each other. I multiplied by something, I divided by something, right? They're not reciprocals. That's not what we did, but they are inverse functions. And I never had to find theta to do so. Okay, we're going to do a couple more like that. This one actually has the arc sine. We always start on the inside, right? The arc sine of negative 5 over 6. So in terms of drawing my triangle, which quadrants do I need to be in for sine? 1 and 4. This one says it's a negative angle, a negative value, so it's going to be in quadrant 4. So I'm going to draw my picture for my triangle down here like this. And my theta, always back towards the origin, is right here. Okay, so in thinking about rewriting this, I now have the sine of theta is equal to negative 5 over 6. Okay, the negative can go on the top, can go on the bottom. We'll actually determine where it is in a minute. So I didn't mean to draw it in such a way that inferred that it had to be on the negative or on the 5. But sine is opposite over hypotenuse, right? Everybody good with that? Okay, so the opposite of this angle theta over here is going to be my 5. And the hypotenuse is going to be my 6. 5 is not measuring necessarily the distance, but I did go down, right? Like my y value, where I'm located right now, is a negative y value. So the negative is going to go on the 5 because I've gone down into quadrant 4 instead of going up. It's going to be a negative value. You can also know that your hypotenuse will never be represented in a negative fashion. The hypotenuse always is the length. But these lengths that I'm putting on the sides of the triangle aren't really lengths. They're supposed to be the x and the y values of an ordered pair. So that's why I'm using the negative 5. I don't have a Pythagorean triple for 5 and 6 here, which means I really do need to use the Pythagorean theorem. So the Pythagorean theorem says that I have a squared plus b squared equals c squared. C is my hypotenuse, so that's my 6 squared. The negative 5 can be viewed as a or b. It doesn't really matter. It's technically negative 5 squared. Of course, that's the same thing as 5 squared. So this one's 36 on the right, 25 plus b squared on the left. If I subtract, I get 11, and my b value would then be square root of 11. Technically, it's positive or negative, but it's representing the x distance along the top of this triangle. So is it positive or is it negative? It's positive because of the location of where x is. This is on the positive side of the x-axis as opposed to the negative location on the y-axis that I put my negative 5 in. So in my triangle, this is now square root of 11 along the top of my triangle. And using this triangle, now I'm going to find the tangent of theta. So tangent is opposite over adjacent. Opposite is going to be negative 5. And adjacent is going to be square root of 11. And we don't leave the square root of a constant in the denominator. We're going to rationalize it. So this is going to be negative 5 square root of 11 over 11. It says the first truly ugly answer we've had. Okay, we're going to do one more, and then we're going to pause, and we'll talk about what I'm going to do with the rest of the lesson, okay? I'm guessing you probably know, but we're going to pause it anyway. Keep going. Last example for today in class. Notice on this one, the angle inside, right, or the value inside, I shouldn't say it's not an angle. The value inside is not a number on this one. It's a variable quantity, correct? Okay. We do it the same way, though. We're still going to draw a triangle. It's just that because we don't know if it's a negative or a positive, we're going to, by default, draw it inside of quadrant 1. Okay? So as I draw my triangle, my default triangle, because I don't know that I need to be drawing it in quadrants 2 or 4, is going to be down. It's going to be up here in quadrant 1, so to speak. And my angle measure is still going to be theta right here. And if I want to think about this, this is secant of theta is equal to x. I don't really like the x here because it's not representing the value x like on the grid. I think that's not what it is, right? But that's the letter that they've used. If you want to change it to a different letter, feel free to do so. But again, we're back with secants, and I don't really think in secants very well. So I'm going to rewrite this in terms of cosine. What would this be in terms of cosine of theta? 1 over x. It's just a reciprocal, right? Secant and cosine are reciprocals on the left. So I get the reciprocal of x on the right. It's 1 over x. And cosine is adjacent over hypotenuse. So the adjacent angle to theta, remember adjacent is always going to be a horizontal or a vertical. It's not going to be the hypotenuse. Okay, the hypotenuse, the bottom part is x, is right here. It's always the longer side, the side opposite the 90-degree angle. The adjacent side then to theta is going to be the one along the bottom, and that's a 1. Okay, so far so good? Third side of the triangle. Just like I did over here, I used the Pythagorean theorem, but I had numbers. Here, one of the Pythagorean a, b's, and c's is going to be x. That's okay. It still works the same way. So a squared plus b squared equals c squared. The c is the hypotenuse, and that's my x squared. And then the 1, put in either location for a or for b, is going to be 1 squared. So clearly 1 squared is 1. And if I want to solve for b squared, which I do, I'm going to move the 1 to the right with the x squared. And then I'm going to square root. Do not make the algebra faux pas of trying to square root each of the individual pieces. We cannot do that, right? There's nothing we can do to simplify this. It is what it is. So up here in my triangle, this piece is the square root of x squared minus 1. And I want the sine of theta for this piece. Sine is opposite over hypotenuse. So what is the opposite side of my angle theta? It's that one I just found, right? Square root of x squared minus 1. And what's the hypotenuse of my triangle? X. And this expression might be worse than the one before. Maybe it's not, I don't know. But this is my answer. I'm done at this point. Now, I think it's probably worth noting that let's say, for instance, that I had been asked, instead of to do sine over here at the beginning, I'd asked to do cosecant. So my answer here had been the reciprocal of this. It had been flipped upside down. Okay? If this were flipped upside down, I do not need to rationalize the square root. The reason I don't is because there's a variable underneath it. We rationalize square roots when there's numbers only underneath them, not when there's variables. And the reason is because depending on the variable value, it might already be rational. Right? Depending on what x is, this might already be a rational number. So that's why we don't do it. This one doesn't have that feature at all. Okay, so here's what I'm going to do. I'm going to pause the video. We've done the hard part, by the way. Everything else after this is much easier and much quicker. It's derivatives of what we've been doing, okay? We've done the hard part, the trig, the remembering all the things. I'm going to go back when we're done, right after class is over and you're done with your gateways, and I'll finish recording the derivative portion. When I post it, I'll post you an announcement that tells you where to start to finish the lesson on the derivative part. Good? All right. All right, welcome back. So we're actually going to move into the calculus component of this now. And the calculus component is the derivatives of these. And as I mentioned in class, I won't have you memorizing these, but they do occur in some nice pairings. So the derivative of arc sine and arc cosine are the same except for a -1. So they're 1 over the square root of 1 minus x squared and -1 over the square root of 1 minus x squared. The same thing's happening with arctangent and arccotangent. These should be on the same slide. It would look a little bit clearer, but the arctangent is 1 over 1 plus x squared, and arccotangent is -1 over 1 plus x squared. And then arcsecant and arccosecant, again, in these nice pairs, is 1 over the absolute value of x times the square root of x squared minus 1, and the same thing for arccosecant with a -1 on top. So we're going to make use of these derivative formulas, and we're going to find 3 derivatives. And all the other derivative formulas that we've had before are going to apply, and we'll take a look at our first one. So our first one is the derivative that we're going to find of the arc sine of t squared. So of course you're remembering that the t squared is an inside function. So when we take this derivative, we're going to have the derivative of the outside, the derivative of the inside. So the derivative of the arc sine is 1 over the square root of 1 minus x squared. But our x is t squared, so it's t squared squared. And then it's times the derivative of t squared, which is 2t. We'll clean this up a little bit. We'll put the 2t on top. And then we have the square root of 1 minus t to the 4th on bottom. All right, the next one's a little bit more interesting, a little bit more going on. On this one, we actually have a natural log function and we have an arctangent function, though they're not intermixing together. So our natural log function, as you know from doing your derivative test, is 1 over what's inside of it, which is t squared plus 4 here. And the derivative of the inside function would be 2t minus the 1/2. Okay, arctangent is 1 over, and it's 1 plus x squared. So I have 1 plus, and my interior for x now is t over 2 quantity squared. And then we times the derivative of t over 2, and t over 2's derivative would be 1/2. Let me write that a little bit bigger. There we go. Now, believe it or not, these are going to completely kind of condense down into maybe an unexpected result in a moment here. You didn't know that natural logs and arctangents were so closely related, but they are in terms of their derivatives. So we'll start with a 2t over t squared plus 4. And then over here, I have a 1/2 at the beginning and a 1/2 at the end, so that's a 1/4. And then I have 1 over. Actually, let me put it as a dot. I think it might be easier to see this in a moment. 1 over, and I have 1 plus, and this is t squared over 4. So we're multiplying fractions. So we multiply numerator times numerator and denominator times denominator, right? So this is still 2t over t squared plus 4 at the beginning. And we have 1 in the numerator for the second piece. And now I'm going to have 4 plus, and then when I multiply the 4 times t squared over 4, I just get t squared. And lo and behold, the two denominators now match, which means I can combine them. So this is 2t minus 1 over t squared plus 4, or you could say 4 plus t squared. So they condense and clean up very nicely. And then our last one combines two different trig functions that we've seen before. We've got arc sine going on here. That's our newest one. And then we have a product rule, right? I mean, it kind of looks like maybe there's a derivative that's going to involve a quotient rule, but it isn't because it's just a constant on bottom. If you want to think about this last piece as being written, and I will think about it this way, as 1/2 x, and then 16 minus x squared to the 1/2. That's how we're going to treat it here in a moment. All right, but at the beginning, we have the arc sine. So we've got 8 as a constant multiplier. Arc sine is 1 over, and it's the square root of 1 minus the x value here, which is x over 4 squared, times the derivative of the inside of, that is, of the x over 4, which is 1/4. And then over here, I've got the product rule. So I have the first piece. I'm going to put it in brackets here. The first piece, 1/2 x, times the derivative of the second. So I'm going to bring my 1/2 down, rewrite the inside to 1 power less, the power minus 1, so negative 1/2, times the derivative of the inside of 16 minus x squared, which would be negative 2x. Okay, I need some more space. I'm going to shift this all over a little bit. And then I need the other half, so plus the derivative of the 1/2 x, which is just the 1/2. And then I rewrite the second piece as is, so 16 minus x squared to the 1/2. Or you could rewrite it in the square root form if you wish. All right, so if you were doing this on a gateway, which you're not, of course, you'd leave it there. So we're not. We're going to clean it up for sure. And I'd like to notice a couple things, that this 8 and this 1/4, these combine together to be a 2. So we'll put a 2 on the top here. My denominator is actually the square root of 1 minus x squared over 16. We're not going to leave fractions inside of fractions, so have no fear. We'll clean that up in a little bit. Over here on the other one, I'm actually going to do some consolidation of some things as well. So in particular, let's see, what do we have here going on? I have, let's see, I've got a 1/2 and a negative 2 here. So those are going to cancel, except for the negative. And then I've got an x and an x right beside them. So I have x squared. And it's still a negative. I'll leave this inside the brackets for a moment. I'll distribute my negative in a minute. Oh, I've got another 2. I didn't see that one initially. Okay, that's all right. This 2 right here will stay in the denominator, right? Because it didn't have a cancellation partner. So we'll leave 2 down here in the denominator. And then I've got a 16 minus x squared to the negative 1/2. So that's a square root, but in the denominator of 16 minus x squared. Because that's the whole first piece kind of mushed back into the same thing. And then on the second piece, I have that same square root, 16 minus x squared, but it's in the numerator now, the 2 in the denominator. It looks like that. Okay, so obviously we're going to have to distribute our negatives through. So let me actually do that now. I'll do it in red. So this negative will change these like this. And I want to get, well, several things, right? So the first fraction, I don't want there to be a double fraction, right? Like the x squared over 16 in the denominator of the denominator. The second piece that's in the brackets, I want to combine these to have the same denominator. So the denominators, let's start with the first one. On the first one, I really need this 16 to go away. And so I want to multiply by 16, but the 16 is underneath the square root. So really what I'm multiplying by is the square root of 16 so that can be combined. And if I do it to the top, square root of 16, that's another 8, right? So, I'm sorry, it's going to be 4 from the square root. The 2 at the beginning is going to make it an 8. So this piece right here is 4, and then 4 times 2 is going to give me an 8. So I have 8 on top. And then when I multiply through the denominator, the 1 becomes a 16, and then the x squared over 16 simply becomes x squared. And you might notice, hey, that looks a lot like the denominator, at least portion of the denominator in the next piece. So now this is a positive. This one already has everything in it it needs for the denominator to match the next piece. So it already has the 2, has the square root of 16 minus x squared. This one over here, which is a minus, is missing something, right? So its denominator needs to have a square root of 16 minus x squared in it. So I'll do that to the denominator and numerator of the the third fraction, I guess, really. So in the top, this 16 minus x squared times itself will now be 16 minus x squared. The denominator will match. It'll be a 2 square root of 16 minus x squared. And you might notice that there is no 2 on the first piece, so I'll multiply the 2 on the first piece. I'm going to copy this to the next slide so we have a little more space to work. Okay, that's what we had from the line before. So what I had there, let me see here. It was an equal sign there, not a negative. Okay. So this said equals. Okay, I think I've got all the pieces now. Clean up a little bit. Okay, so that off there too. I have 16 in the first piece. All the denominators match now, so I'm just going to write them down. It's a 2 square root of 16 minus x squared. So 16 in the first piece. I have a positive x squared from the second fraction. And then this one is going to distribute the negative through, which is going to make this become a negative and this a positive. So now I have negative 16, and I have positive x squared. So obviously my positive and negative 16s are going to combine and cancel. I'm going to end up with a 2x squared on top over the 2 square root of 16 minus x squared on bottom. These 2's are going to divide to 1, and my final result is going to be x squared over 16, square root of 16 minus x squared. So keep working as you simplify. They're not always going to simplify so nicely, of course, as the last two did, but it's hard to know until you start working through it what will and won't simplify.